All right, today we are going to decode a secret language. Seriously, it's used by scientists to talk about everything from the sheer size of the universe down to the width of a single cell. It's the language of scale, and it all starts with a really simple but powerful idea. So let's dive right in.
Just look at this number. It's got 25 digits. This is the mass of our planet Earth in kilograms. I mean, trying to even say it is a mouthful, let alone write it down or, try to use it in a calculation. It's not just awkward, it's practically useless.
Okay, so that was huge. Now let's swing to the total opposite end of the spectrum. This tiny number here, that's the approximate diameter of a single red blood cell, in meters. And again, it's just so clumsy. Counting all those zeros is just begging to make a mistake.
So yeah, we've clearly got a problem. These numbers describe the world around us, but they are an absolute nightmare to work with. So you've got to be thinking, isn't there a more elegant, a more powerful way to handle them?
Well, of course there is, and it's called exponents. This is the power shorthand we've been looking for. A really simple, kind of brilliant way to write repeated multiplication and finally tame those wild numbers.
So, how's it work? It all boils down to three key terms. First, you've got the base. That's the big number being multiplied. Then you have the exponent, that little number up top that tells you how many times to multiply the base by itself. And the whole thing together, the base plus the exponent, we call that a power. Let's look at a super simple example. Instead of writing out 5 times 5 times 5, we can just write 5 to the power of 3, or sometimes you'll hear 5 cubed. The base is 5, the exponent is 3. It's just a compact way of saying multiply 5 by itself 3 times, which, of course, gets us 125. So much cleaner, right?
Okay, so now that we've got the basic idea down, it's time to build out our toolkit. And these aren't just boring rules from a textbook. Think of them more like math cheat codes that let you slice through complex problems in just a couple of steps.
First up, the multiplication rule. This one's a breeze. If you're multiplying two powers that have the exact same base, you just keep that base and add the exponents together. It makes total sense when you think about it. You're just counting up the total number of times the base is being multiplied.
And you know, what's the opposite of multiplication? Division. So you might have guessed this one. When you divide two powers with the same base, you just keep the base and subtract the exponents. It's the perfect flip side to that first rule.
Now this brings us to what's called the power of a power rule. What happens when you take a whole power and then raise that to another exponent? Well, you just keep the base and multiply those two exponents together. Easy enough.
All right, so our toolkit is looking pretty solid for positive numbers. But this is where things get really interesting. And maybe a little weird. What in the world does it mean to multiply a number by itself, 0 times? Or even stranger, -2 times? Let's start with 0. The rule itself is simple. Any non-zero number raised to the power of 0 is always, and I mean always, 1. But why? Well, think back to our division rule. What's 5 squared divided by 5 squared? Anything divided by itself is 1, right? But using our rule, it's 5 to the power of 2 minus 2, which is 5 to the power of 0. So, a to the power of 0 has to be 1. It's like the great equalizer of math. Now, for negative exponents. And this isn't about negative numbers, it's all about following a pattern. Check it out. 10 squared is 100. To get to 10 to the power of 1, we divide by 10, which gives us 10. To get to 10 to the power of 0, we divide by 10 again, and we get 1. So, to get to 10 to the power of -1, we just keep the pattern going and divide by 10 one more time. And that gives us 1/10. And that little pattern perfectly shows us the rule for negative exponents. A negative exponent is just a math instruction that means flip it, or take the reciprocal. So a to the power of -n is really just 1 divided by a to the power of +n. It's not negative at all, it's a fraction.
Okay, we've learned the definitions, we've got our toolkit of rules. Now it's time for the fun part, putting it all into action. Let's go solve a real problem.
Okay, so here's an expression you might see in a textbook or on a worksheet. And at first glance, yeah, it looks a little messy with all those letters and numbers jumbled together. But with our new toolkit, we can clean this up no problem.
Let's just break this down. Step 1, we're going to group the like terms. Put the numbers with the numbers, the a's with the a's, and so on. Step 2, we multiply. 3 times 2, that's 6. For the letters, we use our product rule. A times a squared becomes a to the power of 1 plus 2. B times b is b to the power of 1 plus 1. And step 3, We just simplify those exponents and bam! There's our clean final answer. 6a cubed b squared c. See, our rules made that look easy.
And that brings us to the final payoff, the whole point of all this. Remember those ridiculously large and small numbers we started with? Now that we've mastered exponents, let's go back and tame them, once and for all.
The tool we're going to use for this is called standard form, or you've probably heard it called scientific notation. The whole idea is to rewrite any number as two parts, a simple number between 1 and 10 multiplied by a power of 10. This is pretty much the ultimate application of exponents.
And just look at this. The mass of the Earth, with all 25 of its digits, becomes this clean, simple 5.97 times 10 to the power of 24. And the diameter of that tiny red blood cell? It becomes 7 times 10 to the power of -6. The intimidating has become manageable. Now that is the power of exponents. So, you see, exponents are way more than just a math trick. As we've seen, they are the secret language that lets us clearly and efficiently describe the true incredible scale of our universe.
So, what are the big things to take away from all this? First, just remember that exponents are a powerful shorthand for multiplication. Second, the laws of exponents are your personal toolkit for making hard problems easy. And finally, standard form is how we use that toolkit to handle the gigantic and tiny numbers that define our world. We've talked about the Earth and a red blood cell. But what about the distance to the sun, or the charge of a single electron, the size of a bacterium? Now that you know the language, what else can you go out and translate? The universe is waiting.